Take a look at this ticker tape calculation right here. I mean, it looks entirely logical, doesn't it? The math seems perfectly laid out. But guess what? It scores an absolute 0 in the Cambridge 625 physics exam. Ouch. So, is this terminal velocity calculation actually correct? Well, right now, we're going to pressure test this exact type of answer until it completely breaks. You know, if you've been losing marks on practical papers and you just aren't sure why, it usually comes down to hidden assumptions about measurement and timing. Today, we're tearing down those common mistakes and, more importantly, reclaiming your lost marks. Okay, let's dive right into this. We are looking at a classic 0-mark student response on the left. We're going to break down exactly why this fails so spectacularly. And then, step by step, we'll rebuild it into that perfect top-band examiner answer you see blurred out on the right. Because the core issue hiding in that 0-mark answer, it actually relates to how we humans interact with time. And that brings us to reaction time error. Honestly, this is the painful mistake students make over and over and over again on the 0625 exam. They just assume that if they use a standard stopwatch to time a fast-moving object, the time they get is purely the object's time. They completely ignore the delay between their eyes seeing an event happen and their thumb actually pressing the button. 0.5 seconds. I really want to punch in hard on this number because it is the absolute limit of accuracy achievable when a human uses a stopwatch. It's literally a physical limitation. If we're trying to measure a time interval of less than a second, like, say, an object suddenly entering freefall, human reaction time completely corrupts the data. We simply cannot ignore it. So how do we actually bypass this massive penalty? Well, here's a brilliant workaround. If we need to time something fast but repetitive, like the swing of a pendulum, we absolutely shouldn't time just one swing. Instead, we measure a longer interval, say 10 full oscillations. Then, we simply divide that total time by 10. This drastically minimizes that 0.5-second human reaction error, giving us a highly accurate average, or mean, period. But wait, what if the object isn't swinging back and forth? What if it's actually accelerating in freefall? Well, in just a moment, I'll show you the hidden ticker tape anomaly that Cambridge examiners love to use to trap you. But first, you need the 4-step framework that makes spotting that exact clue completely automatic. So here is the high mark framework that is going to structure literally every practical investigation response you write from now on. Step 1, identify the underlying physics concept. Step 2, pull the exact evidence or data straight from the prompt. Step 3, apply scientific reasoning to connect that data right back to the concept. And step 4, lock the whole thing in with precise examiner wording. Let's see how this brilliantly illustrates the right way to measure rapid motion. Now, for rapidly changing measurements, like an object reaching terminal velocity in freefall, human reflexes fail entirely. You literally cannot use a stopwatch. Instead, you've got to specify that you're using an automatic timer, a ticker tape timer, or maybe a photo gate and data logger. Why? Because these devices trigger electronically, completely wiping human reaction time right out of the equation. Now, what's really interesting about this data table is right here in the middle. Take a close look. It's for an accelerating object, right? Time is increasing steadily by 0.1 seconds. Velocity is increasing smoothly from 1.0 to 2.0. But look at the 0.3 second mark. The velocity suddenly spikes to 8.5 meters per second before dropping way back down to 4.0. We've just uncovered a hidden trap. This right here is an anomalous result. So why on earth did it spike out of pattern like that? Let's apply our 4-step framework to fix it. Concept: objects in freefall accelerate smoothly until terminal velocity. Evidence: well, the table shows a sudden massive jump to 8.5 meters per second at 0.3 seconds. Reasoning: this breaks the expected acceleration pattern, which indicates a likely error in reading the ticker tape dots or maybe a miscalculation of the interval distance. Examiner wording: identify 8.5 meters per second as an anomaly due to measurement error and exclude it from the final gradient calculation. Boom, full marks for sure. All right, it is challenge time. I actually want you to pause this explainer for a second and consider this exact scenario. A student measures one single book page with a ruler that has a precision of 0.5 millimeters to find its average thickness. Based on what we've just learned about timing, try to predict the fatal flaw in this distance measurement. Seriously, pause and think about it. Okay, did you catch it? The flaw is exactly the same as our pendulum timing mistake. A single page is vastly thinner than the 0.5 millimeter precision of that ruler. Measuring just one single page is guaranteed to give a massive percentage error. The correct method? You have to measure a multiple. Stack 20 pages tightly together, measure that total thickness, and then divide your result by 20. This gives you a highly accurate mean value. Now let's move over to another tricky piece of lab equipment where marks are easily lost, the measuring cylinder. The key focus here is the meniscus, that curved surface of the liquid. The rule for this is absolute. To avoid parallax error, the measuring cylinder must be totally vertical, and you must place your eye perfectly level with the bottom of that curved liquid surface. Now, I want you to listen to this actual, perfectly terrible student answer. To find the time of one pendulum swing, use a stopwatch to time it once. Read the measuring cylinder to find the volume. Wow. This answer is vague, it completely ignores human reaction time, and honestly, it tells the examiner absolutely nothing about how to accurately read the liquid level. So let's fix it. Here is the side-by-side examiner correction. We have got to drop the vague descriptions. The top band answer replaces time 1 swing with time 10 oscillations, divide by 10. It replaces read the cylinder with read the bottom of the meniscus vertically at eye level. Replacing vague ideas with precise, evidence-based methods is exactly what guarantees you those top band marks. It really all boils down to this core rule. Choosing the correct timing device for the specific scale of your measurement is totally non-negotiable for the exam. Minutes or seconds, a stopwatch is absolutely fine. Rapidly changing motion, you've got to use a ticker tape timer. Intervals of less than a second, you must specify an automatic timer or a photo gate. So, the crucial point to remember is this. Always check your practical methods against this mental checklist. Are you using the correct timing device for the scale? Are you measuring multiples for incredibly small values or super fast times? Are you remembering to divide by that multiple to find the mean? And finally, are you always stating that you read a meniscus vertically at eye level? Now, if you follow these rules, you have successfully secured perfect data precision. But here is the final ultimate problem. Perfect knowledge is absolutely useless if you freeze up and cannot structure these answers before the exam clock runs out. Knowing the physics is really only half the battle. Writing it down fast enough is the whole other half. So, the final question I have for you is this. Does your current revision strategy account for these hidden traps, or are you still losing precious marks to the clock? To master the timed answer writing system and rebuild stronger, you need to click the next explainer. And remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.